Digital electronics, activity 1.2.4, sequential logic. This is the 2-bit counter you made with the oscilloscope attached to see the clock signal, the upward positive edge trigger, and then it stays on the high signal for so much, and then has a falling edge signal back to 0. So hopefully you have your document open electronically, the hard copy in front of you, and the oscilloscope plugged in. This kind of got chopped off in the last tutorial video, but this is counting from 0 to 3 in binary. 0, 1, 2, 3, 0, 1, 2, 3, 0, 0, 0, 1, 1, 0, 1, 1. So let's look at this tutorial again. Here's your 4-channel oscilloscope. If you double click it, this is how you set the channels up. So just follow the directions. On the time scale, you want 20 milliseconds per division. On the scale, you want 10 volts per division. On channel A, you want to separate it from the center signal. So we'll raise it up 2 volts. Go to channel B here. I guess we could make everything 5 volts per division. Might be better. And let's squeeze it in there. Channel B, let's go 5 volts per division. Let's keep it at the 0 level. We're not going to make it higher or lower so we could see it. And then the C channel, which I think is your clock signal, 5 volts per division. Let's lower it 2 volts. So you lower it like that. See how it goes up and down. Go back to the A channel. Can raise it up too. So then on your activity, hopefully you have the notes from the previous lessons. Using the markers, measure the period of 3 signals. Use this data to calculate the frequency for each signal. The parts of your digital signal are here. So the period is from rise start of the rising edge to the rising edge, and you have your period t. Your equation for frequency is 1 over t. Make sure you convert time into normal seconds because your multisim has normal seconds. So clock in is your clock signal. Make sure you're on channel C. Time 2 minus time 1 is that many milliseconds. You should go on your own. What you could do is you could also stop the simulation and just measure from rising edge to rising edge. Just do your best. That is the 1 period of the clock signal. A good way to do this actually is to find a place where all 3 have a rising edge. Oops. You might want to stop it. So let's see here. Let's see if there's a rising edge on all 3 of these for the beginning. Going up, going up. I think it's right here. Oh, no, of course it's right here. Let's try one more time. Try and get a full move this over here. Where is there a rising edge on all three right on top of each other? Now it might be hard to get. Well, in any case, I would measure from there to there is your period clock signal, because it starts rising up here. Up, hold down, it starts rising up there. Positive edge signal. For signal B, oh, change it to channel B so your circles are on the right thing. I feel like that is one period right there. There. Change it to channel A, which is clock signal A. You have to determine where your cycle starts. Up, hold on high, falling edge, hold on the low signal. So you need to look at this T2 minus T1 in milliseconds, and then use the equation 1 over T to find frequency. So now, on the activity, you need to create a 4-bit counter shown. So let's see if this can be done. Multisim should turn it off. I would save this. Then do a file, save as 1.2.4. This is now problem 5, which is the 4-bit counter. Turn off the oscilloscope. I think we need it. Okay, so for this 4-bit counter, I want you to lay out 4 74LS, 74LS, 74N gates. And to make our lives easier, we're going to try this from the beginning. So this looks more intimidating than it actually is. I would line all these up, get a couple more indicators here. Okay. Let's get one more Illini orange here. Boom. Close. Rename this to label C, label D. Okay, so, oops. Here's your VCC 5 volts. Really quick, all the 5 volts get hooked up to the PR so you could go like this. This is just standard. Where they get hooked up. Then the CLRs get hooked up to the 5 volt signal as well. So we're going to loop this around like so, here to here, here to here, here to here. Our 1000 hertz or 1 kilohertz, 5 volts, I think 50% duty cycle. Move that here. This gets connected to the first clock signal right here. Then not Q gets connected to the clock signal, because then this becomes the clock signal to that gate. This becomes a clock signal to that gate. This becomes a clock signal to that gate. The output also gets connected to this clock here, or this wire here, so we're going to do that to all 4. Keep this as organized as you want. Like so. And then this D gets connected to not Q over here. So the far right gates, let's connect that to indicator A. This one gets connected to B because these are the binary numbers that'll flash the bulbs. I think that's it. So this is the least significant bit because it's connected to D. So if you want to rename this label D, oh, I guess you can't. So this is DCBA. This is the most significant binary bit. Second most. And this is the least significant bit because this is connected to the far right one. So the chips are lined up opposite of our binary counts. So let's see how this goes. Since it's going kind of fast, I would lower the hertz to maybe 500 kilohertz. Oh, yeah. 500 hertz. Maybe you could see a count. That's a little still too fast. I would make this 50 hertz, 60 hertz. 60 hertz is a period of 1 second. So hopefully you can see a count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, that might be a little fast. Let's lower it to 20 hertz. Let's just see how it goes. Okay. Stop it. Double click. Let's make it 20 hertz. Okay. Hopefully it's slower. So this will count from 0 to 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, and so on and so forth. So from this, hopefully you can create the 4-bit binary counter, find the period. If the frequency is 1,000, use your equation to find period. It's right here. You have the notes for this. 1,000 equals 1 over T. Solve for capital T. Answer number 6. We don't have the proto boards yet, so you don't have to do that. And then you stop there. So create the 4-bit counter. Good luck.